All right, welcome back, everyone. We're going to finish up our discussion finally from section 12.6, right? Our graphs for cylinders and quadratic surfaces. Okay, so a lot of this work, a lot of kind of identifications and preliminary identifications for these different types of equations is going to be held on page 877 from my textbook. Okay, I'll show that screen and also I will try to scan that and get a copy to you as well on the Canvas page. But that's really what I'm banking a lot of the discussion in starting to formulate and identify what types of surfaces we may encounter in these special quadratic forms, okay? So I'm gonna start to share my document and we'll get going. All right, so here we go. For our 12.6 are cylinders and quadratic surfaces. And again, a good reference page to keep note of, and I'll scan this to put on our Canvas page as well. On page 877 from our textbook. All right, and that's from that Stewart Calculus, the 8th edition with early transcendentals. But even if you have the other version, it should be roughly the same, the non-early transcendentals, okay? But looking at that page, I know it's a little bit of a glare here. It talks about the different types of surfaces, and depending, as we'll talk about today, our variables, which one has a different sign, which one might be linear in that variable. We get these shapes, but maybe oriented, right? Opening along the x-axis instead, y-axis, so on. But this is a good page to reference in terms of those surfaces, okay? All right, so let's get going in that discussion once more, okay? So from that page, we can start to identify. And when we start to look at these different types of equations for these surfaces, there's some key references that we need to know. So let's go look kind of equation by equation. So for our ellipsoid, make sure I get my spelling right. So for that ellipsoid, okay, and this kind of figure, we're identifying that this is basically, right, an ellipse in each coordinate plane, right? So as we start to take those different slices, those different traces, level curves we'll talk about later, we're going to see an ellipse in those different planes. So let me start off even in this respect, rather than our typical XY plane. But if I have my Y, Z plane, okay? So in that YZ plane, we're going to get an ellipse where maybe has a shorter, that minor axis along the Z axis. Along the Y axis, we'll have that more major axis, right? That longer stretch for our ellipse, right? If they're the same distance, that's when we get a circle, right? So in that plane, that YZ plane will have an ellipse. Likewise, zoom in a little bit. If we were to start to bring in that x-axis in the xz plane, and again, now this is where that 3 dimension starts to get a little bit weird on us, right? We have another ellipse. So in that xz plane, maybe we're going to looks like so. Okay, maybe off to the side here, I can draw that. Or this is like my xz plane. We're going to have an ellipse there, right? What we had just mentioned. In that YZ plane, we'll have an ellipse there. So then as I start to take that, imagine kind of sliding that through. I don't have that 3D animation, sorry, but bringing that over, we can start to get that shifted, okay? And so then as we start to take those different slices, take those different components, okay? We can look at the XY plane as well, okay? Y plane, right? And we'll get an ellipse. You know, I know as we break those down, it might be a little bit confusing, of course, but we're just trying to layer these pieces together, get this framework. So that way, in that XY plane, right, we're going to get these different ellipses. And so as we start to go through, I can kind of imagine that we're getting this kind of framework of ellipses and that Z Y plane here, we're going to get these kind of bodies of ellipses. And again, I know it's a little bit jumbled here. My apologies. Okay. But at the end, once we start to kind of piece those together, we're going to get this framework of all these different ellipses. And we're going to get that kind of football-like shape. Okay. Trying to get those to kind of look decent for us. Okay. But either flat-wise, right in that XY plane, those kind of stacking, like I think about that little kid's donut toy, right, where all those levels stack up, right? I'm thinking about that going upwards, firewise kind of inverting, going down, and then doing that on its side as well, right? There's these XZ, we're going to kind of get these smaller and smaller ellipses, even in the back, okay? And we're going to get that kind of egg-like shape, okay? And so for that ellipsoid, getting into it, our equation, x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1, right? There's our equation for that ellipsoid. And what I wanted to kind of get across in this discussion, I'm going to start to zoom in, pardon me. But what we start to notice here, some characteristics. So when we start to go through these problems where we're given an equation and we want to identify what surface that will be before we get into writing this kind of standardized form, but we notice that all variables involved are quadratic, right? Thinking about those degrees, they all have degree 2. They're all being as their highest exponent being squared. Okay. All those variables, all those terms that are being squared, right, have the same sign. All positives, most likely. If they're negative, negative x squared, negative y squared, negative z squared, so on. We just have to worry about adding to the other side, bringing those terms, rearranging, or multiplying through the entire equation by a -1, so on. And we'll see they're all sharing the same sign. Okay. And then as we start to work on those, when we start to build up those traces, letting z take on different constants. Z equals 0, z equals 1, -1, +2, -2, so on. And we start to compute, each of those is going to be an ellipse, right? Doing the same thing, letting y be 0, y be 1, y be -1. All of those resulting equations, looking at that format, an ellipse, right? So looking at that equation, I start to imagine, like, if I take out a variable, that remaining equation is an equation for an ellipse. And no matter which variable I remove, it's going to be an ellipse. And so when you start to do that work in checking, taking those traces, letting x, y, or z take on a particular value, you'll start to get the ellipse. And at some stage, when you start to let that value get too large, right, when z equals 5, 6, 7, right? When it gets big and you start to move that constant term over, you might get a negative, okay? And again, I know this is abstract at the moment, but play around some numbers, we can see we might get a case when we get like x squared plus y squared equals -2, -5. And because they're both positive squares, we know we can't square something and get a negative. We're not going to add two positives and get a negative. So that's going to be here. Okay, we don't have any points. We don't have any values that satisfy that. And we're not going to get any values. That's where we can kind of start to see where that ellipse may end. You just get one single point that can satisfy. Anything beyond, we're not going to be able to plot. But looking at our equations, even in the most general form, if you see that we have all the variables involved, x, y, and z being squared, quadratic, all they have the same sign. And likewise, one last piece I'll put here, right, equal to 1, right? That's your constant term in your equation. That's going to inform us that we have that ellipsoid, okay? And so then looking at some of these other figures or their shapes on that page, okay? The next step, kind of going through, trying to get through all of the quadratic pieces. Let's look at the cone. Okay. And so for our cone, looking at our shape here, just out of ease. Oh, sorry, it's not X, this is our Y. So used to doing that with our graphing. With our cone, right, it's going to be both sides, both the upward facing cone and downward facing cone. And we'll talk about which direction that cone will open based on our equation format in just a moment. Okay, so in this case, for the cone, let me start off with this discussion. For a cone, what we're going to see, again, all our variables are quadratic. But in this case, we'll see that one variable, one of those terms, has a different sign. And we'll see that in discussion in just a second. And lastly, we'll have that the equation equals 0, right, when all variables on one side. Okay, let's slide this up so we can read that all. Okay. And so exactly, so if we start to see in these equations, right, like here, get my variable right, sorry, x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 0, right? That might be a format it takes on, or we can arrange it to be all terms one side, all quadratics equal to 0. Notice one of those variables, in this case the z, different sign. And of course we can rearrange that to make it x squared over a squared plus y squared over b squared is equal to z squared over c squared. Imagine adding that term to the other side. Okay. And again, similar, if these two are negative, this was positive, right? Add those two terms over so that we get positive z squared over c squared equals, now, if these are both negative, adding them over, now they become positive, looks just like this. Okay. So in that format, all of our variables quadratic, two have the same sign, one has a different sign, equal to 0, right? We'll get that cone shape. And my discussion here, whichever variable has that different sign, right, that one negative, that cone will open along that variable's axis. Right, and so in that example, if this is the negative, the one different sign variable is going to open in that z direction. If it was the x that was negative, or that were equal to here, x squared over a squared, right, then it open along the x-axis, and the similar for the y. And so the idea is that when we start to think about graphing once again, making those traces, okay, in this format, notice this kind of looks like an ellipse. In this equation, this looks like an ellipse. So as long as this quantity over here is some positive value bigger than 0, right, in those xy planes, we're going to get ellipses, right, slowly but surely opening up wider and wider. And since they're all squares, they're always going to be positive. The only time it's going to be equal to 0 is if all three variables are 0. So that's where we're getting the origin as that point where our cone kind of meets. Later, if we start to see some problems where we have to do complete the square, if there's a linear x term, you have to complete the square, and it's just going to shift where that point, where that kind of center, if you will be located. All right. But then when we start to see those other types of equations, when maybe we let x or y be a constant, right? So when you start to see equations in this form, let's say, take the square root on both sides, you have a linear equation, right? And again, if we start to let y be a constant, you're going to be like z minus 5, z plus 2, something like that, right? You'll have that square root going on in simplifying. But that's where we get those straight lines marking those solid edges, the body of that cone, attaching those ellipses that we talked about previously. Okay, so that's where we start to get those equations for the line by incorporating that square root. And again, you kind of have to play around with it to get those expressions to take the square root nicely, but that's where it's kind of coming from. All right, so that's our cone. Next up is going through and kind of remarking how I'm identifying the particular surfaces. Okay, the next one's going to be our hyperboloid. Make sure I get that spelled properly. Of one sheet. Okay, and again, that idea of one sheet is just basically, right, we can use one piece of paper, one sheet of paper, to kind of create that surface, to mimic, to make our kind of model for that surface. Okay, and so let me put that graph in. What we start to see is that we're going to get in some of those planes these kind of hyperbola, right? And hyperbola are those kind of pairs of arcs facing away from each other. Okay, depending what plane we're looking at. And then in other planes, other traces, we're going to get kind of an ellipse, circles connecting that body, right? So we're getting that kind of tube, but now it's going to kind of squeeze in, an hourglass, if you will, type of figure. Okay, and again, not want to put too much, but again, you can imagine having another hyperbola facing that would kind of get that full 360 view. Okay, And so for that hyperboloid of one sheet, what we're going to notice in our equation, and maybe I think that, okay? But with our hyperboloid of one sheet, what we start to see, let me write my equation once more. X squared over a squared plus y squared over b squared minus z squared over c squared is equal to 1. All right, so again, now this looks a lot like the equation we just talked about, that cone, but now notice the big thing, we have a 1 here, okay? So our comments here, right, all variables are quadratic. One variable has a different sign. And now our equation is equal to 1. Right, all of our terms, all of our variable terms on one side equals to 1 or a constant. You can divide by that constant to simplify. But that's going to be the important kind of factor, component, that's going to make this different than the cone, which we just talked about. Okay? And so again, as I start to look at these, when we start to think about those traces, when we have those equations, if I drop out one of my variables, the y variable, x squared minus z squared equals 1, right? That's a hyperbola. Going back to our conic sections. Okay, y squared minus z squared, again, another hyperbola. But then letting z take on a constant, x squared plus y squared equals 1, that's going to be that ellipse circle that's opening up along that z-axis, okay? And so again, like we talked about before, that hyperboloid right, is going to be kind of, I'll say, runs along the axis of the variable with the different sign. Okay, so in this case, right, since it's a negative z, it ran along, it opens up, okay, it goes along that z-axis. Had it been the x, then it would have been opening, it would have been kind of running along the x-axis. So all right. So I should say here, not a different sign, but negative. Okay, and I'll say here 2 positive quadratic variables. There, that's a little better. One with a negative, because as we're going to see on the next discussion, pardon me, is where this changes. Okay, so as I hyperboloid one sheet, that one piece of paper we can make to make that little tube like a cylinder. Okay, so next up, our hyperboloid of 2 sheets. Right, and now in this case, we're going to start to see that our surface that we're talking about is separated into 2 pieces, into 2 separated bodies. Okay, and so as we start to look at that, what we'll start to identify is that in certain directions, right, we're going to get these hyperbolas, sorry. Okay. And again, it might be going that way here, downwards there. But then elsewhere, we're going to start to see, again, an ellipse, a circle, starting to tie those components together. Okay, and again, the bottom looks a little bit weird. But these kind of like two satellite dishes, if you will, facing each other or away from each other. So they're downwards facing hyperbolas. And then as I start to make those XY slices, we're getting those ellipses or circles, so on. That's our equation here. Negative x squared over a squared minus y squared over b squared plus z squared over c squared is equal to 1. So in this case, again, all variables are quadratic. All of them being raised to the second power. But in this case, we're going to have two negative quadratic variables. One positive, right? So again, two with the same sign, one with different sign. This time the two that are the same are negatives. And then again, our equation is equal to 1. Right? So in that case, we'll see those two negatives. And so what the idea is when we start to think about those traces, right? One positive, one negative, that's going to be a hyperbola. One negative, one positive, right? Another hyperbola. But then we start to see here with these negatives, these both share the same sign. This is going to be like an ellipse. But because it's negative, it's going to be a little bit different. So what we need is to make sure that as we start to solve that, that we can make this other side of my equation negative as well, right? Or basically when I move these two terms over to get x squared over a squared plus y squared over b squared positives, that when I bring the 1 back over, that this is going to be positive as well. So depending on the value for z, that's where we start to see the kind of climbing or falling. Z has to be big enough to make this equation valid so we can find those other pairs. Any place where we're going to get negatives equal positive number, there's no values to fill, it's undefined, we can't do that, so that's where we get no points. But once that z is big enough, and we start to move terms over, so on, then we start to get a defined solvable equation, and that's when those ellipses start to form, to build up that set of traces, okay? And again, just like before, whichever variable in that grouping has a different sign, that one positive in this instance, that surface will be oriented, right? Will run along, will open along that variable's axis. Okay. All right. So that's a hyperboloid of 2 sheets. There's 2 negatives, 1 positive. Go to 1. And that finishes out the discussion in terms of all those quadratics, right? So now we're going to start to see where we have a linear term involved. So now this next figure in the elliptic paraboloid, right? So kind of looking at those names, we're going to see our equation for an ellipse at x squared and y squared equaling 1, right, with those denominators, but also a parabola. And what's the equation for a parabola? Like y equals x squared. That means 1 linear, 1 quadratic. All right. So in that kind of idea, thinking about the naming, the type of equations we can deal with, right? In different planes, we're going to have parabolas. And then at some stage, we're going to get an ellipse to kind of connect those pieces. Bring in this kind of bowl-like shape, right? Or to me, it kind of looks like now like some of those frisbee golf goals, right? You ever seen any of those? But again, it's kind of bowl, this base going upwards. And our equation discussion here is that we're going to have two quadratic variables, one linear variable, right? One variable that has its highest degree as one only. And in this case, we'll see typically that our equation equal to 0. Right, and so in our example here, we have x squared over a squared plus y squared over b squared minus z over c equal to 0, right? Or like this. And maybe another component is that we see that our two quadratic terms share the same sign. Okay. Another big component there. Okay. But again, as we start to look at this, depending on that value for z, let's start here, when it's positive, right? That's going to look like an ellipse. If it's negative, we can't have two positive, right? Two squares, positive, be equal to negative. So that's why there's no values down below. But then when I start to remove one of the variables, replace it with a constant, x squared z, right? That's a parabola. A parabola. And all this value that we're choosing, x being 1, 2, 3, is just taking that parabola, kind of shifting it outwards, raising it up, okay? Increasing that y-intercept, so on, or z-intercept, I should say. How it's kind of going along that field, okay? And again, here, that paraboloid, will open in the direction of the linear variable. All right, so the z is linear, so that's where it's opening in the positive z direction. Having a negative z, it'll be going downwards along the negative z axis, okay? And then lastly, that the last figure that we'll address from that page, okay? Hyperbolic paraboloid. Right, so now we're going to see some hyperbolas. And this one is like, right, a saddle, we'll call it, for riding horses, or it's like a Pringles chip, right? But in one direction we're arcing downwards, then I take the plane the other direction, we're arcing upwards, and connecting those different pieces, right, with parabolas, those different figures. Okay, all right. So with that said, let's look at our equation. We're going to have here squared over a squared minus y squared over b squared. I'll make it minus z over c equal to 0. Or likewise, x squared over a squared minus y squared over b squared is equal to z over c. Slide that over, sorry. But with each of these, right, notice what we have. We have two quadratic variables. With different signs. One positive, one negative. One linear term, one linear variable. It could be positive or negative. Again, that's just going to change the way it's oriented, whether it's facing downwards or upwards along the positive z, negative z, or it could be along the positive x, negative x. Okay, and then lastly, our equation in that format, right, is equal to 0. Meaning as we start to isolate variable terms, we get the 0 on one side. It can be equal to another constant. That's just going to create some shifts there. Okay, shifting where that center of that figure might be. But that's going to be kind of our standardized form here. Okay, and so as we start to look at this form, again, depending on this value, when z is that positive, x squared minus y squared, that's hyperbola. Okay, but then z equals negative y squared, right? A downward facing parabola. Over here, x squared z, upward facing parabola. So I actually should change my language for earlier, that it's going to be these kind of bodies of parabolas connected with a hyperbola. There we go, better. Okay, and so in that kind of drawing, if we start to imagine those different traces, letting y be a constant in those xy planes, okay, we're going to get a series of parabolas. And as we start to take that y to be certain values, right, adding that over, okay, right, letting it be on here, doing that work, it's going to start to sync and shift those parabolas. Okay, and so here, case, make sure I get my labeling right here, my xz plane. That. Okay, and then in our yz plane, okay, z equals that negative y squared. Right, we're going to get those parabolas opening downwards. Okay, we're going to get this. And again, it's kind of mismatch here. But as we start to slide, as y or as x takes on these different constants, okay, x takes on different constants, we're going to get that negative y squared with the positive value. So it starts to get these bodies here, okay? And as you kind of see, we start to get this kind of flow. That saddle, again, I know it's a little bit hard to visualize here, starting to arc downwards. But again, the image, so I'll leave it to that to save myself here. We get that kind of saddle right in that YZ plane, those parabolas, XZ plane, and we can start to connect those with obviously our hyperbola arcing upwards. Okay, but again, I know it's a little bit awkward there. We start, or probably our hyperbolus, we start to slice it here in that XY plane. You see the arc of hyperbola, like so. Okay, and again, that one will take some time to develop. All right, but with that said, a lot to take in. These are the kind of statements, though, that I'm really looking at and identifying, right? And so in practice, in that section 12.6, right? Likewise in the end of chapter practice, we can start to look at some of these problems here, for instance, okay? So taking those concepts of what we're looking for the nature, for the characteristics of these equations, and we start to look at these problems like 21 through 28, okay? I know it's a little bit fuzzy, a little bit out of focus. There we go, trying to get that to lay still, to be focused, okay? We can start to look, so in this case, right, number 21, all quadratic, all the same sign, equal to 1. That's going to be an ellipsoid. Similar for number 22, all positive, quadratics, equal to 1, another ellipsoid. But based on those coefficients, right, dividing by an LCD, so on, we can start to see kind of how wide, how compressed, in which direction, right, is going to have the length of those major or minor axes, right, which direction is stretching. The bigger the denominator, the longer, the farther it goes out in that particular variable's direction. So when you divide by, in this case, since these have coefficient 9, 4, we divide by 36 everywhere. Okay, and we can start to see those directions. 23, x squared minus y squared plus z squared equals 1, all quadratic, equal to 1. 2 positives, 1 negative. What's that going to be? Right? So again, I start to think back to those statements we had. All quadratics, okay. 2 positive, 1 negative, quadratic. All variables quadratic. 2 positive, quadratic variables, 1 variable is different sign, negative. Equation equals 1. That's a hyperboloid of 1 sheet. So that's the kind of set of steps, the kind of discussion, thinking we're going to go through as we start to identify. And then with work of completing the square, doing some of the algebra steps, dividing by the common multiple of our coefficients, right? We'll get into a more standardized form for our equations, shifting sometimes if we need to complete the square, where the center of those figures might be. Okay? All right, leave it there for now. I know that's a lot of information, but again, our saving grace, that page 877 in our text, that table giving us that valuable information of what these equations and surfaces, more importantly, will look like. All right. Thanks for your time. If you have any questions, definitely let me know. Let me stop sharing here. Questions, concerns, email me, let me know. All right, take care.